So once again, I would like to thank ISP for their cooperation, and the University of Rwanda for hosting my stay. The title of my presentation is Weighted Cauchy-type Fractional Differential Equation. And the content of this is a breakdown into 6 parts. We start with some introduction, we proceed to definitions and basic properties. Then we face some theorems in this platform, such as always is the case, uniqueness theorems and some inequalities, which are of Gronwall-type. And then we'll see estimates, especially these estimates are relative, and we see property of solutions, positivity. After that, we'll take an excursion to estimates of derivatives and stability of solutions. And finally, we'll validate all these theories that have been developed by finding some areas where it can find life. So in this regard, we have an application in population models due to Volterra. So we'll finally see fractional population model in a closed system that has been earlier developed by Volterra. So now we'll go to motivation. This study has been started long back. In 1954, Barrett studied this fractional linear differential equation, d alpha ut is equals to lambda ut plus f of t. Alpha is, in this case, when Barrett studied, alpha he considered to be complex, and he made some assumption on the real part of alpha. Indeed, he considered the real part of alpha to be between n minus 1 and n. So that means alpha is always assumed to be a fraction. So when n is 1, it is obviously between 0 and 1. So in his study, in an attempt to find the property of solution of this one, he assumed that this f of t, which is the forcing term, if it is absolutely integrable on AB, then the solution of this fractional differential equation is unique. That is what he concluded. And then Al-Abedin in the year 1978 studied the nonlinear problem. While Barrett studied linear, this one took the nonlinear problem, and he took alpha to be real. So he resided on the real axis between the half-closed interval 0 and 1. And with this condition, again, he assumed continuity of f in both variables and Lipschitz continuity with respect to the second variables. Under this assumption, he has shown that the solution exists, and furthermore, it is unique. So he established existence and uniqueness. Whereas in Barrett, it was only uniqueness that has been established, and he didn't say anything about existence. Following Al-Abedin's work, and then Del Bosco and Rodino in the year 1996 studied this fractional autonomous problem. The right-hand side f this time depends on the unknown function u alone. There is no explicit dependence on t. Alpha this time he considered to be in the open interval 0, 1. He didn't consider alpha to be equal to 1 as opposed to his predecessors. So in his study, he makes the following assumption. He assumed that f is 0 f of 0 is 0, and furthermore, f is Lipschitz continuous. With this, we have shown again existence and uniqueness. And then earlier in the year 1965, Al-Bassam considered similar problem, but this time non-autonomous, non-linear. Alpha, he allowed it to include 1. And in Al-Bassam's study, he didn't use the technique that the other used. Instead, he went to tools from analysis, in particular, a fixed point theory. So by appeal to Banach fixed point theorem, he tried to establish the existence of the solution. And further, what he has done is he also considered the autonomous case. And in that case, he considered an eigenvalue problem, which means d alpha ut is equals to lambda u of t, fractional eigenvalue problem. And then he tried to study the eigenpairs, the properties of the eigenpairs, eigenvalue and eigenfunction. And his paper is, I think, now available online. And then Lakshmi-Katan and Vasta in 2008, they considered again nonlinear fractional problem, this time alpha between 0 and 1. This time what they have studied is they didn't focus only on existence and uniqueness, but on the property of solutions. They tried to see if there is oscillation, in which case they are tried to look at the zeros, if at all exists, and they discussed that, and their paper, I think, is already published in the same year. In 2008, I think it's available. And then next to Lakshmi-Katan, we still have other researchers, namely Neugebauer. Please, the next slide. Islam and Neugebauer in 2020, they have considered this nonlinear problem with a weighted initial Cauchy condition, and they now diverge from the other's approach. In that, they first try to transform this into another fractional problem. They have tried to convert this into Volterra integral equation, and the entire study is confined to the study of the corresponding Volterra integral equation. And in that study, they have established existence as well as uniqueness. And recently, in the year 2022, Karimov et al., Karimov, Michael Rozansky, and Tokmaga-Betov, they have studied this fractional linear problem. Their basic task was to study this under various boundary conditions. In that, in the investigation, they come out with the observation that the weighted Cauchy-type problem is less studied, less understood. And they said that, okay, as compared to the others, the arsenal of literatures is very few, and they documented this on their paper that is published in this year. So their study is basically investigating this problem, not with a specific boundary condition, but various boundary condition with Dirichlet, with weighted Cauchy, and the others. And finally, they compared the focus and eventually conclude that the weighted Cauchy type is less represented. Now, this is this being all about the motivation. Let's now get the definition. The fractional integral, in the sense of Riemann-Liouville, is expressed in this form. Here, alpha is a real number which is positive. Usually, people study by restricting alpha between 0 and 1, and the others like Kilbas and Odelby, they sometimes pay attention to the other fractions in an effort to study for alpha is equals to 3/2, or say the others, they consider alpha between 1 and 2. There are situations in which they also consider between 3 and higher numbers. So in all, it is given by this here. Gamma of alpha is the usual gamma function. So this can also be seen as the convolution between two functions, f of s and the other function that carries the exponent. Having defined the fractional Riemann-Liouville fractional integral as such, we will move to Riemann-Liouville fractional derivative of order alpha greater than 0. This is again given by this expression. The alpha ut is 1/gamma of n minus alpha, dn by dt n, and then you have this thing in the integral. Here again, alpha is always between two consecutive integers. The idea is, because you are studying fractional stuff, we always squeeze ourselves between any two consecutive integers, either 0, 1, 1, 2, 3, 4. But in our case, we reside with 0 and 1. For that, to that end, we have to set n is equals to 1. When n is 1, it is alpha is between 0 and 1. That derivative, dn by dt, is the first derivative. It is just d by dt. This is the formal definition for Riemann-Liouville fractional derivative of order alpha and Riemann-Liouville integral of fractional integral of order alpha. When you move to the next slide, we have some properties. This operator, the Riemann-Liouville integral operator, for any alpha greater than 0, it is bounded in L1 AB, because we are considering infinite intervals. So it has this L1 property. And again, it has this iteration property. If you take Riemann-Liouville fractional integral of order alpha plus beta, you will get the same result as applying a fractional Riemann-Liouville integral first with respect to beta and then with respect to alpha one after the other. This property is also called semi-group property. And when it comes to linearity, for the derivative, one can just pay attention to the derivatives and establish easily the linearity. Here C1 F plus C2 G C1 C2 are constants. F and G are assumed to be differentiable. So when you apply the alpha's derivative to the superposition, you get something, and you may apply the derivative separately to the functions f and g, and afterwards you can superpose them. The linear combination exactly matches with the derivative of the linear combination of the two, which means if you take the derivative of the linear combination of the two, you will end up with a linear combination of their corresponding derivatives. Okay, having said this much about the basic properties, we shall now move to operational properties. These are actually well known. P1, if you allow alpha is already, as we said, greater than 0 by its very nature from the birth date. So if you allow it to get close to 0 from the right, then we have the identity. And in P2, we involve both the derivative and integral of the same order, fractional or derivative of order alpha and fractional integral of order alpha. If we apply them in this order, what we get is this expression on the right hand side. But just from P2, let's skip P3, P4, and go to P5. In P5, if you swap the role, if J alpha comes first and D alpha comes second, then you have the identity. This means J alpha is the right inverse for D alpha. So now going back to two, we can see that they cannot commute. In classical differential and integrals, with the requirement on the boundary, you can interchange the role, but here interchanging is not such possible. In P3, we have the alpha's derivative of f is equals to the derivative of the 1 minus alpha's integral of f. Here one can observe that we can write first alpha as alpha is equal to alpha 1 minus alpha minus 1 minus in bracket 1 minus alpha. So D on the right hand side in front of J is the power of 1 minus 1. You can write its exponent as 1. So you can write single D as a composition of the derivative and the fractional integral, but this time the derivative is the usual classical derivative. And in P4, something interesting, D alpha of a constant. In the classical calculus, the derivative of a constant is 0. But this time, the derivative of a constant is non-zero. This is C over gamma of 1 minus alpha, T raised to minus alpha, where this T is supposed to be greater than A or greater than 0, where the definition of the integral is, or the derivative is stated. Now, okay, now we can go to the next slide. As I said earlier, for instance, when one of the researchers studied this fractional differential equation, he transformed it into the corresponding integral equation, and the whole study was conducted for the integral equation, but the conclusion is applicable to the differential equation. So this statement gives us the feeling of why that was the case. If f is continuous and alpha is between 0 and 1, the weighted Cauchy-type fractional differential equation, as you can see, is equivalent to the nonlinear Volterra integral equation, which means any solution of the differential equation satisfies the Volterra integral equation, and furthermore, the solution of the Volterra integral equation also satisfies that. So they are equivalent. Well, their equivalence can easily be actually established Basically, if you start from the first one, you have to apply from the left J, you have to operate by J alpha and recall one of the operational properties we stated. And finally, you have this condition. When you plug that, automatically you arrive at the integral equation. And if you start from the integral equation, all you have to do is apply the derivative d alpha to u of t. On the right hand, you have d alpha of t outright. So what remains is applying d alpha of t to the right, but then you apply linearity property and also product property, and eventually that will give you the initial condition that is up there. So this way, this statement can be verified. And the next slide, we have now possible groundwork already. Now we'll go to work with what you have already stated. So in this part, the first theorem that comes is about uniqueness in our study. If U and U2 are solutions of this weighted Cauchy fractional differential equation, with the assumptions that ft dot is Lipschitz continuous, we have equality between the two. That means if f is Lipschitz continuous, then they are identically equal. Before we go to the proof of this one, let's recall. In ODE, if you have things like that and f is Lipschitz continuous, then we have theorems that fulfills existence and uniqueness. The moment it is Lipschitz continuous, we have theorem due to Picard and Lindelof that guarantees existence and also uniqueness. And if this Lipschitz continuity is compromised and we simply consider continuity, then the theorem due to Cauchy and Peano guarantees local existence. So in the framework of ODE, we have this. Thus, if, for instance, if we allow, as the other investigators have done, alpha to be equal to 1, then our investigation can also be checked by evoking those theorems that I just mentioned, Picard, Lindelof, and Cauchy-Peano. Now, getting back to the proof of this one, what we have to do first, we have to transform this into the corresponding Volterra integral equation. The Volterra integral equation corresponding to this is already on slide 10. And in that, all you have to do, you assume that U1 is a solution, U2 is a solution, then you superpose them with the coefficients 1 and -1, C1, U1 plus C2, U2. So you have U1 minus U2, and then upon subtracting those two and applying the property of the fractional integrals, you have some terms, and then you take the distance between the two, and then by, I think, yeah, one of the properties, you can automatically establish the uniqueness. So this is just the sketch of the proof. Now, on the 12th slide, we have here we have uniqueness, and the next slide. Okay, now we have this inequality. Basically, in the classical calculus, we have various versions of Gronwall inequalities, but this one is of that type because we are working with fractional order derivatives. So if I take two solutions of this weighted Cauchy-type fractional differential equation with assumption of Lipschitz continuity on F with respect to the second argument with respect to T, then this inequality holds. Here, K is strictly greater than 0 and fixed. So the distance between the norm of the distance between U1 and U2 for any value of T, when we scale it by alpha, it is always dominated by the distance between the corresponding initial data, U01 minus U0 multiplied by e raised to kt. This Gronwall-type inequality, its proof is more or less lengthy. It requires some stuff, but we can basically follow the same proof as in the preceding theorem, but this time we don't use P1. Instead, we use a fundamental theorem of calculus. We use fundamental theorem of calculus and introduce a multiplying factor which is positive for any value of t. That means you have an auxiliary function gamma of t which is e raised to minus kt. This exponential, it always remains positive for a t. So after considering the corresponding Volterra integral equations and superposing them and taking the absolute value, we multiply by this, and then the other routine is actually to notice in the meantime that the derivative is negative, and finally that will tell us that what we have been working with is non-increasing, and with that we can establish the difference to be equal to 0, and so the norm of if the norm of something is 0, then automatically that thing is 0. But in our case, what you have is U1 minus U2 is equals to 0, amounts to say U1 is identical to U2, and that is for every t. Okay. No, K is not a Lipschitz constant. This time, K is indeed, it is taken to be the Lipschitz constant over gamma of 1 minus alpha, specifically. It's not Lipschitz constant. Instead, it is L over F is a Lipschitz constant, so Lipschitz continuous. We take L from that and divide it by the gamma function, gamma of 1 over 1 minus alpha, gamma of 1 minus alpha. That way we can establish. Okay. Now we have comparison. Assume that F is this time be a little bit relaxed. It is continuous. U1 and U2 are solutions of this alpha fractional integral equation in the sense of Riemann-Liouville, and we restrict again our alpha between 0 and 1. Well, as we know, this integral equation already earlier we have seen that is equivalent to the alpha fractional differential equation. Now, if okay, something is missing from this one, I have to. So eventually, what we have to show is alpha minus alpha. What is missing is correct. If U1 naught is in this blank, if U1 0 is less than U2 0, if their corresponding initial data are unequal, then the derivative of this near t equals to 0 is less than 0. But this one, again, from the linearity, one can outright say that their derivatives are also unequal in that order. For the proof of this one, yes, please.
I didn't get what you said about what is missing on the if.
U1 0 less than U2 0. The initial data. Here you have, you see, UT is equals to
Okay.
U0
Yes,
T
yes.
raised to alpha minus 1. So that U0
Yeah.
introduce to that the subscript 1, which means this is corresponding to the solution U1. Again, to that U0 introduce suffix 2. That is to say, this is the initial data corresponding to U2. So if the corresponding data for U1 and U2 are unequal, that means U1 0 is less than U2 0, then this is the conclusion.
Okay,
Did I answer?
clear.
Okay.
Yes, yes.
Thank you. Now, in the proof of this one, it is really obvious, because if we treat the earliest proofs, this is just a repetition of all those steps with the use of P2 and observing that the relationship that we said, G alpha now comes with D alpha, as we earlier said, G alpha, D alpha. D alpha, G is not the left inverse for D alpha, it is only the right inverse. So we have to observe this. So if we are able to establish then by P2, that will automatically follow. What remains is just manipulation. So in those steps, we can conclude the proof of this one. Okay, let's move to the next slide. So this is something about relative estimates. Okay. We have this time a pair of weighted Cauchy-type fractional problems of the same order, alpha. The first one, the right-hand side is F, that depends on two arguments. On the right-hand side, we have G, that depends again on two arguments. These two agree on the initial data. Limit at t approaches 0 from the right, t1 minus alpha ut is u0, and limit at t approaches null from the right, t1 alpha wt is also u0. Now we assume various conditions for G and F. G, we just assume it to be only continuous, while for F, we impose Lipschitz continuity with respect to the second variable and continuity with both variables. If we have L1 function, say that the difference between F and G is dominated by phi of t for any positive t, then the difference between their respective solutions, W and U, satisfies this inequality. So the name relative is in that we are first considering G to stay in the vicinity of F so long as it is allowed by phi. So by the goodwill of phi, if G resides close to F, then the solution that come out with the use of G can also be forced to stay in the vicinity of W with this inequality. Here, what we want to emphasize is when F is Lipschitz continuous, from uniqueness, we have already seen that the first the first differential equation, alpha fractional integral equation, has already a unique solution. It has exactly one solution, but the one to the right can have multiple solutions. So among all of all these possible solutions, if we can choose the one that shares initial condition with U, then their difference is dominated as such. So that is the story. Why we use two differential equations together. Yeah, the right-hand side the solution exists, but we don't know about the uniqueness. Existence is certain. But for the one with F, existence and uniqueness is also certain. So among those that solves the right-hand side, we speak about those which share initial data with this. In the proof, again, we have to transform both of these into the corresponding alpha fractional integral equation, which is the corresponding Volterra integral equation, which is indeed nonlinear. So we superpose them, and after a few manipulation and maybe evoking some of the operational properties, we can eventually arrive at this inequality. Okay. Now we always work with positive. Why we always need positive solution? You see, in real world problems, when we model, why we fix initial data? Because we want to pick physically relevant solution among multiple solutions that exist. And why we need positive solution again, it has to reflect reality, to capture physical phenomenon in the world around us. So we usually require solutions to be positive in most of the cases. For this case, it makes sense to shed light situations under which one may have a positive solution. So for this nonlinear alpha fractional differential equation with Cauchy data, the weighted Cauchy data, if F is continuous, that means F is a map from 0, 1 to the right ray, 0 to infinity, including 0. If F is from 0, 1 to 0 to infinity, if say that it is non-decreasing, this assumption, imposing this assumption on F, if additionally U underscore and U bar are continuous on this compact interval, say that for the U with over bar, this inequality holds, and for U with under bar, we have this. Now, if let again the limit as U runs to infinite f of tu, for each t, if this is finite and stays above 0, say that U lies between the two, U underscore. But then, if the initial data are unequal in this order, automatically U is greater than 0. It means the solution is positive. Let me go. This is the proof of this is a little bit lengthy, so I skipped it. Let's skip this one. Next slide. Now, estimates of derivatives for continuous function and the solution of this alpha fractional integral equation. First, if U is absolutely integrable on 0, 1, then it is alpha's derivative weighted with this coefficient is also absolutely integrable on the same interval. And second, if F satisfies this gross condition, for each t, and where g is continuous, then we have the derivative of t alpha u less than or equals to gu, and the proof is again just manipulation and mere substitution of change of variables for A, and for B it is product rule. We apply the fractional version of the usual product rule, and we can establish that. Next slide. Okay, now all the theories are in place. So let's see where on earth these theories can find a home. One possible avenue for this is just population model. So the fractional, the weighted Cauchy-type fractional Volterra model for population growth in a closed system is given this way. Here, d alpha ut is equals to alpha ut minus bu squared minus c ut 0 to t, and the parameters a, b, c. A is the birth rate per capita, and B is the self-crowding term, and C is the parameter, the measure of sensitivity for toxin. This basically models in a closed system if a toxin or something erupts, how it affects the entire population. So C is like that. And in this case, if we choose these three parameters in such a way that this expression is less than 1, where eta is supremum of ut on the interval 0, 1, and u is a corresponding solution, then u remains greater than 0 if we have initial seed. If we have initial as a first generation, then there will be no extinction. If u naught is greater than 0, so u forever remains greater than 0. We will see the next slide completes the whole discussion. We have the proof. Well, sorry. The proof, you see, I was lucky instead of always pouring words. So this time you can read the proof. First, we have to take the right-hand side to be equals to f of tu, because what you have is d alpha ut is equals to all these three terms on the right. So you denote this by f at tu. Now you bring in u and v, take their difference, superpose them, apply absolute value, then automatically that's what you have. And then you integrate both sides from 0 to 1, and then you apply Fubini's theorem. And upon applying Fubini's theorem, you automatically establish this one. So to come to Fubini on the inequality, you have to introduce an integral from 0 to 1. So here, as you can see, a plus 2b plus c eta, if it is less than 1, the conclusion is that f is forced to be Lipschitz continuous. But then Lipschitz continuity implies uniqueness of the solution. Now, if u naught is 0, automatically u is 0 throughout. So by uniqueness, 0 cannot correspond to u. So this concludes the proof. Let's proceed now to references. Okay, summary. Well, again, the summary you can see, the moment alpha is 1, by the way, the earlier fractional problem reduces to the integer order Volterra population growth model with Dirichlet data. And if the sensitivity parameter is 0, then we have again weighted fractional logistic model. The logistic model, due to the Pere Verhulst, I think he's from Belgium, you remember it, how he modeled Maltesian, how he improved the Maltese model. So it reduces to that Verhulst model for C is equals to 0 and alpha is equals to 1. The moment alpha is allowed to be a fraction, then we have the weighted fractional version of that. Next slide. Next slide, please. So these are our references. Still our reference some still other literatures in the next slide as well. These are some are from 1965, and we also have until 2022. So it is based on this that we are able to write this. The next slide. Okay. By the way, this is part of the ongoing joint research work with current PhD students at my home department in AAU. Their name is listed as such. So these 3 PhD students, they are involved in the study of fractional differential equations, and with various concentrations. Okay, next slide. Okay. I acknowledged already those of you who come for attending. Now let's thank the ISP for what they have done, and I also thank IPMS PDAAP, which actually support the research between researchers in different universities. And I also thank my own home department and the University of Rwanda for cooperation. And having said this, finally, thank you all.